Okay, so let's work this this example of elastic potential energy. And in this example, we have a spring-loaded gun, basically, and this spring drives a plunger, and we want to calculate, basically, the spring constant of this plunger. And we're given some information in the problem. So here's the initial situation. We have some gun, and we have a spring here, and that spring is compressed, and it drives some plunger here. And the plunger has some mass, we'll call it M. Okay, and we'll kind of make this gun a little bit longer here. And there's some equilibrium position for the spring, and so this is compressed by a distance x. And we're given that value x for the problem. So that's our initial situation. We'll label that I for initial. Now the final situation, our gun now has this spring is now pushing the plunger. And we're told that what the plunger's maximum speed is. And the maximum speed of the plunger is going to be when that spring has pushed the plunger to equilibrium. Okay, so there's our plunger now, mass M. Okay, so it's pushed that now to equilibrium. Okay, we know that that's the maximum speed there because as this plunger stretches the spring, it's going to start slowing down because the spring's going to start pulling on the plunger now. So, so this is where we have our maximum speed, and we'll just call that V to make things easy. So it has a speed V out there. Okay, so we can apply conservation of energy to this problem to solve for the spring constant, because that's what we're really asked to do. So, so since there's no friction involved in this problem, conservation of energy tells us that initial kinetic plus initial potential energy is equal to the final kinetic plus final potential energy. Okay, and we can right away simplify this expression. So first of all, we're starting with the mass at rest in our initial situation here. So the mass is at rest. So the kinetic energy in the initial situation is 0. So we can eliminate that right off. Now what about the final situation? Well, we have kinetic energy because the plunger is in motion now. But the spring is now in its equilibrium position. And the potential energy of the spring is 1/2 kx squared. So if this spring is now in equilibrium position, its potential energy is now 0. So the potential energy in this final situation doesn't apply to the problem. Okay, so the potential energy of the spring, remember, that's our initial potential energy, compressed to a distance x. The potential energy is 1/2 kx squared. That's our initial potential energy. Final kinetic energy, the plunger is now in motion at a speed v, so it's 1/2 mv squared. Okay? So we're given the compression x, that's 0.015 meters, that's given. Okay, that's given in the problem. The mass, we won't write it down, but the mass is given as well. The mass is 0.05 kilograms, and the velocity at top speed, that is 20 meters per second. So we're asked to solve for k here, so we want to get an expression for k. So the 1/2s cancel. Divide both sides by x squared, and what we get is that the spring constant, k, is equal to mv squared over x squared. Okay, so we plug these values in. The mass, again, is 0.05 kilograms. Velocity 20 meters per second. And don't forget to square that. Divided by our compression, which is 0.15 meters. And that's squared as well. So solving for K then, when you do this arithmetic here, what you get is the number 889. And the units for the spring constant are in newtons per meter. And that's the case if everything else is in its proper units. Mass in kilograms, velocity in meters per second, x in meters. And what you would see when these units cancel out is you would have newtons per meter. The other way to see that that's the unit for K, remember this force of a spring is negative kx. Okay? So if F is newtons, x is meters, K has to be newtons per meter. Because you multiply newtons per meter times meters, and that gives you newtons.